Okay, so here's what we were talking about last time. We're talking about Gram-Schmidt orthonormalization. Again, really big word, sounds scary, but ultimately it's not that deep of an idea. I mean, roughly, other than normalizations, other than dividing vectors by their own magnitudes, right? The big idea is to identify, for a given vector, for a given vector, what is the part that you don't like? Right? I don't like the part that's pointing in the direction of my existing orthonormalized vector. Identify what that vector is, the part that you don't like, throw away what you don't like, right? Thus resulting in a vector that is at least pointing in the direction that you do like. That's the heart of it. That's the big idea. And then, of course, you have to normalize at the end. Right? If you have multiple previously fixed vectors, so you've already fixed the first two vectors, so these are already orthonormalized, then just realize that there's kind of two parts there. I mean, this vector that I don't like, it's not pointing in the right direction. Partly I don't like it because of the extent to which it's pointing in the V1 direction. And partly I don't like it because of the extent to which it's pointing in the V2 direction. So instead of throwing away the one part that I don't like, I throw away the two parts that I don't like as relates to the two previously fixed vectors. Throw those away, just like we talked about previously. So throw away that blue part, throw away this orange part, and then you're left with just something that is pointing in the correct direction. And then you can normalize at the end, of course. Okay. So that's the big idea of Gram-Schmidt orthonormalization. There's a certain amount of formulas and such. But really the thing to make sure that you remember is this formula right here. That, how do you identify what specifically it is that you don't like about how one vector is pointing in the direction of another vector. And easy argument about projections computed with dot products, inner products in general, and directions defined by, those existing normalized vectors. So make sure to remember that formula, make sure to remember the overall big strategy, and it's just a bunch of details. So that's where we're going to pick up this time. I'm not going to go through all the details of this calculation because it's a tremendous amount of arithmetic. And y'all can do arithmetic, right? I'm going to let y'all wade through all of the ugliness of here. But note the structure. That second vector that we don't like, the way I fix it is I identify the part about it specifically that I don't like, namely to what extent does it point in the V1 direction. Right? Subtract that off. It's a certain amount of arithmetic there, dot products and scalars and blah, blah, blah. Subtract that off from that second vector that I started with, and out comes my direction fixed second vector. Okay, which of course then you normalize by dividing by its own magnitude. Okay, so this is the one little trick that I do want to talk about that's not just sort of like take a deep breath and plow forward. This idea, so I've got a vector and I would like to normalize that vector. I'd like to divide that vector by its own magnitude. You can do that. Notice that's what I did here. I swept under the rug quite a bit of arithmetic, but I found the magnitude of that x2 vector right there. Yikes. Okay. And the arithmetic I swept under the rug, just look at it. There's fractions and non-trivial numbers. It's kind of a pain, right? Here's the tricky idea. When you do that, when you divide a vector by its own magnitude, what you get is exactly the same as what you would have gotten had you multiplied that vector by any positive scalar and then normalized. Right? So the unit vector pointing in the direction of the blue vector is exactly the same as the unit vector pointing in the direction of the purple vector. The only difference between the blue vector and the purple vector is I multiplied by a positive scalar. So punchline, multiply by any positive scalar you like before you normalize and save yourself loads of trouble. So, for example, in this case, how about, I'm just thinking about my own sort of, personal sanity. How about I just multiply by 49? Wouldn't that be nice? Just multiply by 49. Let's normalize that resulting vector. It doesn't have any fractions in it. That looks a lot easier. Right? And you will get the same result. So anyway, I encourage you to look for opportunities to do that down here in this next example. Now, just real quick, just structurally, let's observe that, we identified one part that we don't like. We identify a second part that we don't like. We subtract both of those. A lot of arithmetic ensues, blah, 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 right? But you get down to that x2 vector, right? That's what you have to divide by its own magnitude. Same story. I can multiply by any positive scalar that I would like. Doesn't matter. Right? So I'm going to first multiply by 5 because I don't like fractions. I could normalize that vector instead. Gets me to the right answer. No problem. But look, check this out. Even more laziness. How about I multiply by 1/4? I'll multiply by 1/4. And that gives me 0, -2, 1. And we normalize that vector. That was even easier. Right? So use this trick whatever clever ways you feel like is going to make your arithmetic easier. Everybody see the idea? Okay, everything else is details. Okay, so going along. So I have to do a little bit of review here. I have to rehash some things that we've already talked about in order to segue into the new topic for today. So we've talked about vector spaces previously. And I'll remind you, our definition of a vector space specifically defines something called vector spaces over the reals. Going back in the notes, here's the page where we defined vector space over the reals. And among many other requirements, of course, notice that one little detail is that scalar multiplication specifically was scalar multiplication by real scalars. This real scalars here is what we mean when we say over the reals. Now, the book kind of swept all this under the rug. I was sweeping it under the rug too, but at least I wrote it right. The book really just ignored this point. So does this matter? And furthermore, have we been following this rule, or is this just some kind of little formality that we kind of blew off subsequently? And I have to confess, I did this on purpose, but I, on purpose, deliberately blew off this requirement and therefore committed some little math crimes along the way of what we've been doing so far in this class. Like I said, I did it on purpose. The reason I did it that way is because a proper treatment of where this situation came up would have been more worrying about things that at the time would not have made any difference. So this is what I call a victimless crime. Everything that I did that technically a little bit wrong is something that could absolutely 100% be fixed with just a couple of fancy words, right? I just didn't want to throw out those fancy words while we were busy thinking about other things. So let me show you the situations that I'm talking about where we broke our own rule. We multiplied by non-real scalars. The first one is here in chapter 4 when we were looking at solutions to differential equations. And remember we had this deal where we have these complex valued functions that come from complex roots of the characteristic polynomial. And we took these functions, we rewrote them like this. Specifically, I wrote those solutions as linear combinations of these solutions. Linear combinations, you'll note here, with a complex scalar. So strictly speaking, based on how we wrote things down, we're not allowed to do that at that time. All right, now, so you probably see what I'm talking about here, that, we were busy. We were thinking about, there was all sorts of other, difficult ideas that we were dealing with at the time. There was so much else going on, and I think it would have been a distraction for me to, get upset about complex scalars at that time, when in fact it would not have made any difference in the calculations. Everything that's in these notes here is perfectly fine in the sense of it's fixable, right? So no problems there. You don't have to sort of cast doubt onto our previous results. But there's certain things that should have been said before we did that. Here's the other instance where we broke this rule. Complex eigenvalues and complex eigenvectors. Remember, this matrix here has a complex eigenvalue and a corresponding complex eigenvector. And so, for example, here AV is equal to lambda V, and this scalar is not real. And we're not supposed to do that, as we have our definitions of vector spaces set up at the moment. Okay, so again, reminder, this is all fixable, nothing to worry about. Okay, so I swept it under the rug, again, because we had so much else that we were worrying about at the time. Okay, so what I'm going to show you now, though, is, because I must, sometimes this stuff does matter. We're about to get into an area where we really do have to worry about the difference between real and complex. And we can't just kind of, it's just formality, sweep it under the rug. So I'm going to start off by trying to persuade you why it's important to worry about what your scalars are. And here we go. Let's consider the complex plane. The complex plane is a vector space. Not a scary thought, right? I mean, the complex plane, you can add complex numbers. They add like vectors. You can multiply them by scalars. Right? What's the problem? What's the big deal? Let's talk about the idea of dimension. Of what dimension is the complex plane? And now there's a temptation to say it's two-dimensional because it's a plane, for crying out loud, right? It's a plane. Planes are two-dimensional. But check this out. In fact, if you allow complex scalars, the complex plane is one-dimensional. It's a very creepy thought. Here's what I mean by that. Here is a basis, I claim, and I will justify it momentarily. There is a basis for the complex plane. I claim that any vector in the complex plane, I don't care what, well, vector in a complex plane, of course, is just a complex number. Let's call it Z. That, I claim, is a scalar multiple of this basis vector. There is just the one basis vector, the number 1. Right? I claim that there is a scalar that I can multiply by 1 to get Z. If you allow complex scalars, that is, and that scalar is Z. There it is. If you allow complex scalars, this is literally a basis. Dimension is defined to be the number of vectors in a basis, and the complex plane is one-dimensional. Does that freak anybody out? And this is not intuitively satisfying. It's a plane. Come on, planes are two-dimensional. It's supposed to be. So the mere fact that we allow complex scalars is what has created this little nightmare. That mere fact of allowing complex scalars. Okay. Now, everything reverts to being just fine and dandy if you go back to requiring real scalars. Requiring real scalars, that's a basis. A complex number Z is a linear combination of the vectors 1 and I. If you allow only real scalars, then this has to be the number A, the real part of Z, and this has to be the number B, the imaginary part of Z. Right? So, here we have a basis. The basis consists of two vectors. And now the complex plane is two-dimensional again, as it should be, or so it feels. Everybody on board? Any questions about this? It's very unsettling. Okay. Nothing resembling this bad came up or would come up at all in either of the previous contexts where we swept this under the rug. Okay. But you can see here we've got a big problem. Okay. All right, now I'm going to leave as an exercise for y'all to consider this next question. What about CN? So CN is a lot like RN in the sense that it's ordered in tuples, right? RN is ordered in tuples of real numbers. CN is just ordered in tuples of complex numbers, right? So CN, its dimension depends on what kind of scalars you allow. So I would like to suggest as an exercise, if you allow complex scalars, prove that this is n-dimensional. And if, on the other hand, if you require strictly only real scalars, then it is 2n-dimensional. I'm going to tell you a very strong hint on how to do this problem. Obviously, if you want to compute dimensions, you find a basis. Right, so this is, you just need to find a couple of bases. The tools that you're going to use to find these two bases are think very much in terms of the standard basis, and then think about how you would combine the idea of the standard basis with these two ideas up here for how we dealt with the complex plane by itself. Right? So combining those ideas will allow you to find these bases. Okay, it's a nice exercise. Okay, so CN is different. Everything is different. We can't just treat CN like RN. This is we're in a very, very different circumstance, and things are changing, and this just doesn't work. So what I would like to ask now is, what about inner products, and specifically on CN? Right, now let me remind you, where did inner products come from previously? We had previously been doing business in RN, addition and scalar multiplication. Supposed to be using real scalars. And when it turns out that, RN has a kind of attached to it this other thing was the dot product. And the dot product has some nice features and some nice applications and, satisfies certain nice properties. So we defined something called an inner product that was just basically anything that behaves kind of like the dot product, right? I like what happened over there with the dot product. Let's see if we can reproduce that in any other sort of analogous way. So we asked the same sort of question here. Now let's look at CN. Can we do something kind of like the dot product? Can we define an inner product on CN? Okay. Now, with all these warnings from the previous page about how things can go catastrophically wrong, right? You'd be right to be worried. And there is a temptation to say, I don't know, let's just use can we just use the dot product? I mean, the math 212, the plain old, why can't we just use the same thing? And, well, this is just another one of those situations where it really, really different. Things change, and this old formula, this dusty old thing for Math 212 is not going to fit well in CN. It does not. Something very, very bad is going to happen. Specifically, you may recall one of the properties we required. One of the identifying key properties of dot products was that the only vector whose self-dot product is 0 is the 0 vector. That was a big one. And look at this guy. That vector there, that's not the 0 vector, and yet its self-dot product is 0. Okay, so this is super weird. Kind of what this is saying is that the dot product in CN does not behave like a dot product. Right? It just doesn't. This is very unfamiliar. This is not how dot products are supposed to behave. So we are in a tough situation. This old dot product has crashed and burned. It is absolutely unusable in CN. So can we come up with something else? The first temptation you're going to have is, let's think of something, a different formula. Admittedly, obviously we can't use this formula. Let's think of something that, a different formula that will have exactly all four of the properties that dot products that we identified as being sort of the defining characteristics of the dot product way back when. And there is no such thing. So that's unfortunate, right? But the good news is there is something that's very close. So we're going to write down a formula that is is very, very similar looking to the dot product, that satisfies four properties that are very, very similar looking to the four properties that dot products satisfied in the previous context. And it's going to work very nicely for our purposes in CN. So here it is. It's called the Hermitian dot product. Very similar to the dot product. Here's the formula for it. Hermitian dot product. It's a sum of products. I mean, at a glance, it looks exactly like the old dot product. The only difference is you'll notice this conjugation right there. So it's a little bit weird, but this formula, the way we're going to do this is that whatever the second vector, whatever vector is on the right in your Hermitian dot product, the vector on the right you conjugate before you proceed with the old sort of multiply and add formula for dot products. So a little bit weird. Notice the notation that we're using here, this brackets notation, which remember we've already used for inner products. I don't want to use a dot, right? So I'm going to use the book's notation here and go with this brackets notation. But do notice that subscript of H, indicating that this is a Hermitian dot product. So Hermitian dot product, that notation with a subscript of H, and what it means is just don't forget to conjugate the vector on the right. Real quick also, remember we rewrote dot products last time as transposed matrix products. We've never had any need for this way of writing things before last time's lecture, but it just came up that we needed this. So anyway, note that this is just an alternative way of writing dot products, and in this case, conjugating the vector on the right. Again, we have a nice alternative formulation for the Hermitian dot product. Yeah.
By conjugating it, you just mean flipping the sign of the imaginary.
Yep, that's right. So this word conjugation gets used in multiple different ways in math. Yeah. So conjugating in the complex numbers sense, not conjugating in the change of basis sense. Yeah. Great question. Anybody else? All right, now, a common complaint at this point. I'm getting ahead of myself. So notice these four properties. Very, very analogous to the four properties that we identified as being sort of the defining characteristics of the dot product. Do notice that they're not exactly the same, though. In order for this to work, and I just kind of stampled my own thing here. Let's say in order to make this work, notice we don't have commutativity. If you switch the order, you conjugate. That's easily confirmed. It'd be a nice exercise. Confirm for yourself that this formula, this Hermitian dot product, it's not symmetric. It's kind of conjugate symmetric. Also, when you factor out a scalar on the right, you conjugate that scalar. So here it is, this scalar here, because it's a factor on the right, because it's inside of that which is going to get conjugated, if you pull it out, you have to kind of manually conjugate it to be fair. Okay. Other than that, the properties are the same as they were back in the previous section. Okay, how are we doing? Is everybody on board? Any questions? Yes.
What is C? What could C be?
C. Any scalar. Yeah. So any complex or real scalar.
So
yeah.
What do you mean by conjugating on a scalar?
Yeah, so scalars here are complex numbers, and complex numbers, so the complex conjugate, remember, is where you take a plus bi and you turn that into a minus bi. Yeah. So that's what that bar on top means. So I'll refer you back to section 4.2, where we had a bunch of discussion on complex numbers. Yeah, right. Okay. Okay, yeah, so here's a common complaint that students make at this point, myself included, when I was first learning this material. Hey, you're just making stuff up. Right? So can you just do that? Can you just make up formulas? Well, so there's two things to say about that. So one is, well, remember back in Math 212, or whenever it was the first time that you saw the regular dot product, there was a first time you saw that. Right? And, well, it probably seemed pretty weird at the time. Now, since then, you have seen how the Math 212 dot product has nice algebraic features. You can do algebra with it because of those features, right? Those properties that it holds. And it's got connections to geometry and connections to the physical world. So it's natural because of, well, how it happens to describe things that you're interested in. So we're in a situation here where you just haven't seen those features yet of this construction, right? But this is natural in some nice ways. For one thing, here's the algebraic properties. Right? These are nice algebraic features for an operation to have. You can do algebra with this thing. Because what it means to do algebra is to apply established algebraic properties. And we have some. So there's that. Here's another thing about this formula, and I think this is a really important point. It looks like we have made up a whole new thing. But I argue that we kind of haven't really, in a way, and this is going to seem weird, but this kind of is the old Math 212 dot product in a way. Think about what would happen if you apply this Hermitian dot product to a couple of vectors in Rn. Specifically, Rn. If you take a couple of vectors whose coordinates are all real numbers, the conjugating doesn't do anything. And this is exactly our old formula for dot product for Math 212. Right? So, case could be made, and I would make this case, that, this does not look like the formula we wrote down in Math 212, but really, the fault there is with how we wrote it, Math 212. This is the natural way to write dot products. It was kind of a who cares point back in Math 212. In Math 212, there were no complex vectors, and so putting that bar over it would have been, sort of unnecessarily tedious. It never would have affected anything, right? So out of sheer laziness of convenience, we just didn't do it. But really, arguably, we should have. This is the natural dot product. It is what we were looking at in Math 212. And we just wrote it in a lazy way. So arguably, we are not making up something new. We are just finding a better way to write the thing that we've seen previously. Yeah?
So C is a complex number, it's not just a...
Yeah, so this, you're talking about this C right here?
Yeah.
Yeah, these C's, these scalars are allowed to be complex numbers. Yeah, so this is a complex scalar situation. Okay. Yep. Absolutely. Okay. All righty. So, moving along. A couple of little cultural points. You remember when we first wrote down dot products, and then we said, look, anything that behaves like the dot product, as in terms of those four properties, anything that behaves like the dot product, we're going to call that an inner product. And inner products are useful tools in a lot of circumstances. Likewise here, anything that behaves like the Hermitian dot product, we're going to call a Hermitian inner product. And Hermitian inner products can be really useful. You can further generalize. These don't have to be on Cn. You can talk about a construction that behaves algebraically just like the four properties previously about the Hermitian dot product. Anything that behaves like the Hermitian dot product but on any other vector space with complex scalars, we can call a Hermitian inner product. And there's a really important one, and we don't have time to talk about it, but just, again, a nice little cultural sort of connection. Quantum mechanics is done, a certain part of quantum mechanics anyway, is done in a vector space that is a vector space with complex scalars. You view particles as functions, complex valued functions on R3. Call them wave functions. And that is a vector space with complex scalars. And there is a very important Hermitian inner product that acts on that complex vector space. So it's there's a bazillion details, and it's I can't describe it in 30 seconds here. But just culturally, I wanted you to be aware of that. That's where this is going. This idea here of putting the conjugate on the right hand side shows up very dramatically in quantum mechanics. Okay. All righty. Okay, so we're gonna keep going. We're gonna define other odd things that based on what we've got already. So here's a fact from matrix algebra. If you have a dot product, and by the way, this is just a dot product. I'm using inner product notation for psychological purposes that we'll talk about in a moment. But by this I just mean the regular dot product. If inside of this dot product, if the item on the left has a factor of a matrix A, like this, then by way of a certain argument, you can show that matrix is allowed to sort of whip over to the other side as long as you transpose it. So that's what this says. It's a little bit weird, but in a dot product, a matrix factor on the left can move to the right if you transpose it. Now I'm going to let y'all think through this argument here. I'll hit some highlights, but the reason this works is because recall last time we saw that dot products are transposed matrix products. That's all that is. Transposes of products are products of transposes. Old news, right? And you can move parentheses around however you'd like. So, for example, I can group like this, and a transposed matrix product is a dot product. Okay, I guess I did prove it for you. So that's why this works. Neat fact. Another way to say this is that there is a what I like to call a dovetail, a nice fit between the idea of dot products and the idea of transposes. These two constructions, dot products and transposes, fit together in a nice way in that you get this nice formula about matrices moving from one side to the other, like so. Okay. So with that in mind, we've got these dovetailing ideas. If you tweak one of them, right, we're taking the dot product. We now have a modified dot product. We have a Hermitian dot product. Reasonable question, how would you have to modify the notion of transpose to make the new dot product dovetail in just the same way with a new modified notion of transpose? What is it that's kind of like transpose that fits in with Hermitian dot product in this way? And this is just a calculation, but here's the answer. It's this thing called the Hermitian transpose. The Hermitian transpose that we denote with a star. There. In a Hermitian dot product, doing a Hermitian transpose of a matrix allows it to move over to the other side of the dot product. Now, what is this Hermitian transpose? How do you compute it? It's a very simple two-step process. You take the original matrix and you conjugate it. Just conjugate each entry. And then transpose. And, of course, it doesn't matter which of those you do first. Conjugate transpose. Okay, this I'm going to leave as an exercise for y'all to do on your own. The way you're going to prove this fact is you are going to steal. You're going to rip off this argument, right? That allowed us to get from sort of there to there. Just steal that same argument, apply it here, modify it appropriately. Of course, now this is no longer a regular dot product. This is a Hermitian dot product. The way that a Hermitian dot product is a transposed matrix product, well, it's a little different, right? You gotta, don't forget your conjugate there on the right side. So adapt it appropriately, of course, right? But morally, kind of the same argument will get you there. It's a nice exercise. Okay. All right, a little bit of terminology. Just, feel like I have to say certain of these things. This term, Hermitian transpose, I really like this term, Hermitian transpose. It's very, very natural as follows. Where did it come from? Right? Why did we write down this formula? Well, because in the context of how it fits in with a Hermitian dot product, this behaves like the transpose did in terms of how they relate. So in a Hermitian sense, it's kind of like a transpose. Doesn't Hermitian transpose seem like a natural choice of words? I think it's great. Another term that you can use for Hermitian transpose, conjugate transpose. I think that terminology makes great sense because look at the formula. You are literally taking a conjugate and then transposing. Really natural. Everybody on board? Another bit of terminology, just you should be aware. This formula here is also very often called the adjoint. It gets used in other contexts, sort of variations of this. And adjoint's kind of it's a little bit of an easier word. It's fewer syllables, if nothing else. Now, don't forget there was back in chapter 1, there was another thing that our book called the adjoint. And you may recall I made a comment in class at the time that, that's kind of outdated terminology these days. The word adjoint usually refers to this. And that other construction from back in chapter 1, you can call the adjugate, or there's different sort of options, but typically wouldn't call that an adjoint these days. This is an adjoint at this point. Okay, we're going to kind of keep going. With our new notion of Hermitian dot product, we have a sort of a modified dot product. We motivated a kind of a modified transpose, and now I think very naturally we're going to talk about how with our modified transpose, what idea kind of fit in previously with transposes, and how would we modify that? Let's just kind of keep going in this general direction. And there is an old idea that we already saw very strongly connected to transposes, and that's the idea of symmetry. Right? A symmetric matrix is a matrix that is its own transpose. So if we've modified our notion of transpose, there comes along now kind of in effect a new notion of symmetry. Here it is. This is what I like to call a Hermitian symmetric matrix. A Hermitian symmetric matrix is a matrix that is its own transpose. I guess that didn't come off so well, did it? Okay, here we do this like that. A matrix that is its own Hermitian transpose. So I think the term Hermitian symmetric is pretty motivatable, right? I mean, again, in this Hermitian context, trying to make everything fit in to adapt to the modifications that we've made previously. This is the notion that's analogous to the notion of symmetric in the real context. Being as this is in the Hermitian context, I think Hermitian symmetric makes sense. Okay. Nobody calls it that, though. What everyone calls this is a Hermitian matrix. So I think of it as, this is my sort of in my own mind. But like I say, I kind of made that term up. Really, the term is Hermitian. So you just kind of have to remember when you're going through, when you see the word Hermitian, oh hey, here's a Hermitian matrix. What they mean is they mean a matrix which it's in the Hermitian context analogous to being symmetric in that it is its own Hermitian transpose. Okay. Pause for questions real quick. Is everybody cool with that? Yeah.
So a Hermitian matrix is necessarily real.
It is not necessarily real. No. So real, we're going to see momentarily that real symmetric matrices are Hermitian, but there are plenty of Hermitian matrices that are not real. So for example, here's one. So that is a Hermitian matrix in the sense that if you conjugate transpose that, you get the same matrix back. See what I'm saying? Yeah, but it's not real. Yeah. Right. Yes?
How would you conjugate a real number?
Super easily. The conjugate of a real number is itself. Yeah, so the conjugate of a plus bi is a minus bi, and if b is 0, cool. A plus 0i turns into a minus 0i, which of course is the same thing. Yeah. Does that make sense? Anybody else? Yeah?
So diagonalized matrices are
You're getting ahead of us. So we haven't gotten to diagonalizing yet. So right now we're just talking about transposing. Just this right here. Yeah, so we haven't talked about any change of bases or anything like that. Yeah. You see what I mean? Well, okay. So anyway, the question you're asking is just way ahead of where we're at right now. So right now we're just talking about what does it mean to what is the Hermitian analog of transposing? And transposing is just a much simpler construction.
Okay.
Diagonalizing, whoa, hey, that's a big deal. We'll talk about that soon, but not yet. Okay. So, reminder. In the real context, when you move a matrix from the left side to the right side in a dot product, you have to transpose it. But hey, if it's symmetric, it is its own transpose, so you don't have to do anything. Analogously, in the Hermitian context, when you move a matrix from the left side to the right side, you have to conjugate transpose it. But wait a minute, if it is its own conjugate transpose, you don't have to do anything. Just like in the previous case. Okay, so nice feature. Then this is the feature that we're going to use a lot of. Hermitian matrices have the property that you can just whip them over to the other side in a Hermitian dot product and nothing changes. Right? Okay. All right. So that's going to be a useful observation. Now, quick observation: real symmetric matrices are Hermitian. This is a very straightforward observation of, well, if it's real, then when you conjugate it, nothing happens. Right? And then when you transpose it, well, but it's symmetric. So when you transpose it, nothing happens. So the process of doing conjugate transpose doesn't do anything to a real symmetric matrix. These are kind of the world's easiest Hermitian matrices. Yeah. All right. Alrighty. And this has outrageously powerful consequences. We're now going to get into actually proving some results. Up to now, let me confess, we've been kind of exploring through what I like to think of as Alice in Wonderland kind of a situation, because we're dealing with a bunch of familiar ideas, dimension and dot products and transposes and symmetry. These are all things that we've talked about, but in this context, they're all kind of messed up, and it's like cats aren't supposed to disappear, and stuff like that, right? So it's a strange sort of versions of everything that is otherwise very familiar. Now, though, we're actually going to stop just kind of exploring and actually prove some results. And it's shocking how these come up so unexpectedly and quickly. First theorem: if you have a real symmetric matrix, don't forget that means it's Hermitian. If you have a real symmetric matrix, then loosely speaking, the eigenvalues are real, and I'm going to say loosely speaking, the eigenvectors are real. Now, this should come as quite a shock. In fact, you should be a little bit suspicious. After all, we've found eigenvectors and eigenvalues before. They weren't always real. They were complex sometimes. The eigenvectors that we found were complex sometimes. What do you mean they're always real under circumstances that we've never seen have any connection to eigenvector calculations before? Right? Who cares if it's symmetric? Why would that matter, you might think? Right? Now let's think in terms of how would you approach, from a chapter 5 point of view, how would you approach trying to prove this? We guess, let's see, how do you find eigenvalues? Well, to find eigenvalues, you write down the characteristic polynomial. I guess we could write down the characteristic polynomial, maybe because it's a symmetric matrix. Maybe we could argue that the terms in the characteristic polynomial, we could make some sort of combinatorial argument about how the terms must have certain nice things must happen, and then try to algebraically argue that the roots of this nth degree polynomial must, I don't know, something like that. Seems possible, right? But yet horrifying. Maybe we could do that to 3x3s. Even that's non-trivial. I mean, factoring a 3x3, oh gosh, we don't have an equation that we can just plug into. It seems like it'd be hard. For 17 by 17, forget about it, right? We're going to write down a 17-degree polynomial and just start drawing conclusions about all the roots. Seemingly intractable. Okay. Well, this is not only true, but it's easy to prove. Surprisingly easy to prove. Here's the argument. Suppose I have an eigenvalue and an eigenvector. Let's just say. I make no assumptions about the eigenvalue or eigenvector. This eigenvalue, maybe it's complex. As far as we know, who knows? The eigenvector, well, maybe it's complex, no idea. Okay. I'm just going to write down this expression. Note, I'm doing a Hermitian dot product. I kind of have to because we're looking at complex vectors. And considering that A is Hermitian, I can take this matrix factor and I can move it over to the right. Seemingly pointlessly for the moment, but certainly I can do that. Right, we proved a couple pages back that you can do this. Okay, fine, so I move that over there, so what? Well, don't forget we're talking about eigenvectors, eigenvalues, and so I can rewrite AV as lambda V in both of these places, right? Perfectly legal. Now I'm going to factor out the scalar. Let's see here. Factor out this scalar lambda. It comes out as lambda. Factor out this scalar lambda. Don't forget, you have to conjugate when you factor out a scalar on the right. That was one of our rules, right? That was a necessary, part of the deal here in this definition. Is you have to conjugate this factor scalars that come out of the right. Now, where did that come from? Just, by the way, sort of strategically, this conjugation on the right came from the fact that we conjugated the vector on the right. And why did we conjugate the vector on the right? You could argue that it is the act of conjugating the vector on the right that makes this turn into positive, and therefore only 0 when the coordinates are 0. So this conjugation of the vector on the right is essential for making this behave in a plausible way, and an unavoidable consequence of that is that we have to conjugate the vector, the scalars that we factor out of the right-hand side. So that's an important deal right there. And then look how everything falls into our lap. We put that there, that conjugate there, canceled the common factor there, and lo and behold, that's equal to that. Namely, this eigenvalue is its own conjugate, and therefore that eigenvalue is real. Right? I mean, where did this come from? It seems to have just come out of thin air. But there it is. Yeah.
So why can you turn A into lambda V?
Oh, yeah, because by assumption, so we're assuming that lambda is an eigenvalue and V is a corresponding eigenvector. Yeah, that was our starting point. Yeah. How we doing? Everybody okay? Okay. Very weird. But this construction, the big idea here, again, it feels like we're pulling stuff out of thin air. And you can't, can you just pull stuff out of thin air and start making stuff up and then cling to the consequences? Yeah, you can make up any formula you want. Just keep in mind, when you make up a formula, what's really tricky is making up a formula that behaves well, that satisfies algebraic properties, that you therefore can do algebra with. If you write down some arbitrary formula, if you don't have any algebraic properties, you can't do anything. You write something down and you're dead in the water. Right? So the fact that this thing that I made up has nice algebraic properties is what allows me to go somewhere, and, well, it's just kind of a lucky break that it allowed me to go somewhere really nicely, like this. Okay, we will pick up here on Friday. Y'all have a good Wednesday. See you later.